There we go. They're now recording. Okay, so do you guys have any questions? Did you watch the video from Friday? Okay, good. Yes.
I wrote it in my notes somewhere. I wanted to ask you if you could do like more examples of the one in the video where you did like the theta and then A. Like I wrote down all your notes.
Theta?
Yeah.
I don't remember.
Like the example was limit x to 7 power 6 sine to the third x. Like I understood what you did.
Oh, I just plug in.
Yeah, I know, but I just wanted to see more examples.
Okay, we're gonna do like 4 more examples today, but I don't think I'm doing something like that. One is just evaluating. Okay, let's see. So the notes are here. So talking about this is the one for simplification. So no, should be this one. So are you talking about this one, number 2?
Yeah, like I understood it. Like it was fine.
All you have to do is evaluate.
Yeah.
That's it. Everything that's going on here and I was talking about is just to remind you how you evaluate this if you don't remember. Of course, you can just plug this into a calculator. What if you don't have a calculator, right?
Okay. So would we have the calculator?
Yes, but you need this knowledge because.
Yes, I wrote it down. I will have.
So this is what you want me to explain to you?
No. That's fine. I understand that part.
No, it's fine. I mean, all you have to do here, the point here is that most of the functions that you know when you take the limit, usually you just plug in, and that's it. That's what it boils down to. The only thing is that sometimes you will get like 0 over 0 and so on, and then you need to do something about it, okay? But for example, in all of these cases, you just plug in. So here in this limit, you just evaluate the function sine at 7 pi over 6, and then you cube the result, right? That's one of the properties, that if you have a function to some power, when you take the limit, you take the limit of the function, and then you raise the result to that power. That's what we did. So we did the limit of the sine, and then we cube it. Now the question is, because this function, is nice, has no holes, nothing weird. When x is close to this number, the sine is going to get close to whatever sine of this number is. So the question is, what is this? Right? And then here, as you know, you need to see what quadrant is this angle. This happens to be in quadrant 3, because it's pi over 6 more than pi, right? Pi plus pi over 6. So it's over here in quadrant 3, and you know that in quadrant 3 the sine is negative, because it's given by the y value. So, that's why you see a minus here. Now, how do you compute this kind of stuff? If you don't have a calculator, there are some values that you need to know, like 30, 45, and 60. You need to know the sine, cosine, tangent, and all the other functions for those 3 guys. And once you know those in quadrant 1, then you can translate that information from any of the other quadrants, 2, 3, and 4, using the reference angle. What's the reference angle? It's the angle between the x-axis and the terminal side of your angle. So in the pictures here, you see. So I'm doing this. I'm explaining this again because this is important, and this may come up again. You need to know this. So if your angle theta is in quadrant 2, this is your reference angle, okay, between the terminal side and the x-axis. In quadrant 3, this is the angle in quadrant 3. The reference angle is terminal side and x-axis. It's not this guy. It's this one, okay. And in quadrant 4, this is your angle in quadrant 4, and then this is your reference angle. Why is this important? Well, because the theorem says that the trigonometric value of an angle is the same as the reference angle up to a sign. It could be plus or minus, right? Reference angle is always less than 90, so it's always positive. The sine, the cosine, the tangent is always positive. But your angle could be negative or positive depending on the quadrant. In this case, we're interested in sine of 7 pi over 6. The reference angle is going to be pi over 6 because if you look at the picture, that's a relationship, right? So if you have your angle, then you subtract alpha and you're going to get pi. In other words, if you do pi plus alpha, you get the angle. So this is 7 pi over 6. Take away pi, you're going to get pi over 6. That's my reference angle. And I put the minus because remember, this part here is positive, but because we're in quadrant 3, the sign has to be negative. And at this point, you should know that sine of 5 over 6 is 1/2, which is 30 degrees, right? If you don't remember, again, calculate. That's all what's happening here, okay? Again, in most of these cases, all I did was plug in. You know, what's interesting is this kind of examples, and if you have piecewise functions and so on, that we're gonna do a couple now, okay? Good. I'm just trying to figure out what was the problem with this.
It's just like I was watching the video and like I took notes of everything you did, but like in that part you went a little quickly, and I was just concerned about like if I get another question like that, like will I be able to like do it by myself correctly? But I'm sure
just plug in.
Yes, yeah.
Look, if you ignore the blue stuff, just look at the red thing. What did I do? Look at the red steps.
Yeah.
What just happened there? I plug in 7, 5, or 6. That's all I did. Okay. It's easy.
Yeah.
It's just that there are many things going on in the background that if you don't know, then you know that's why I was explaining, because I don't know if you remember this. This is from trigonometry. Okay. Okay. Anyways, the idea is that we're gonna do more examples now, and again, this section here, the one about more techniques, this was very important. Okay, because most of the time your limits are gonna be the ones that you see here. Okay, in many situations, because you know when it's just plug in, that's pretty easy. The interesting thing is, what if you cannot just plug in? So let's go ahead and let's do a couple more examples. Anybody has other questions? Yes.
I was wondering if you could review. I remember you did one question here where you used the conjugate.
I will do an example on that. Okay. Are we good? I will do an example on that. Okay, so again, let's do a couple of examples about the stuff that I talked to you about on Friday. So evaluate the limits. Let's see, the first one, let's do limit. Okay, let me write down all the problems that I want to do and then do them one by one. So this one. And this one. And so here comes one, like the one that you're asking, something like this. So the conjugate technique, you use it whenever you see radicals like this, okay? So if you see the function having radicals here at the top and the bottom, you may want to use conjugate. But first you have to plug in, because if you don't have 0 over 0, there's no need to use conjugate, okay? And then let's do this one. We have the function f of x. Let's do it piecewise. And then let's find the limit as x approaches 0. And then after that one, let's do this one. Okay, so here we have 5 examples. Let's go ahead and let's go through them again. The way that you deal with this basically is what I talked to you about on Friday. Okay, it's just that there are a couple here that you have to think about a little bit before you proceed. Okay, so remember, one of the things that we discussed on Friday was that there are some rules that you can use for limits, okay? So we're not going to be using tables anymore, and we rarely are going to rely on graphs at this point, okay? Today, we're going to talk about limits at infinity, and then in those cases, we will still need to rely on the basic graph that we know, okay? But for the most part, we're just going to use the properties. Like, for example, if we want to do number 1, we see that it is a fraction. The first thing that you do is the limit of a fraction is the limit of the top divided by the limit of the bottom, provided that the bottom is not 0, okay? So the first thing that you do is let's plug in, evaluate, and see what we get, okay? If we get a number, we're done. If we don't get a number, if we get 0 divided by 0, for example, that means that's in indeterminate form, we have to do something, okay? We cannot just leave it like that. If you get a number on top that's not zero and zero in the bottom, we're gonna talk about that today. Okay? That limit may be some sort of infinity. It could be positive or negative infinity. That's one of the things that we're gonna discuss today. Okay? But if you get zero in the top as well, we cannot predict what's gonna happen, so we have to compute. So let's do this. The first one was limit as x approaches 3 of x squared minus 3x over 2x squared minus 5x minus 3. So actually, before I even do this, if this would have been x approaches 0, who can tell me what's the answer? If this was a 0 here, what would be the answer for this problem?
Zero, right?
Just be 0, right? Because the top is 0, the bottom is negative 3, 0 divided by negative 3 is just 0. Yes? So again, the first thing that you do is plug in. Now, let's plug in 3. If we plug in 3, what do we get in the top?
0.
We get 9 minus 9, right? So we get a 0. And what do we get in the bottom?
0.
So let's see. What's this? As 9 times 2, that's 18. Then negative 15 minus 3, that's negative 18. 18 minus 18, that's 0. Yes? So we get 0 over 0. Now, this is an example of what we call an indeterminate form. As I mentioned, there are 7. We're going to discuss all 7 of those later on. Okay? So this is an indeterminate form. And what this means is that when you see this, you cannot predict what's going to happen. Okay? We cannot say, oh, the answer is going to be infinity, or the answer is going to be 3, or 20, or 4. We don't know. We need to do something about it. Now, what do you do? Well, it depends on the problem. In this case, when you have rational functions, the rational function is a fraction with top and bottom are polynomials. Okay? When the problem looks like this, having 0 in the top, what does that mean? From your knowledge of pre-calculus. This means that 3 is a 0 of this polynomial, right? What does that mean? That means that x minus 3 is a factor, right? It's a factor still. So you can write this as x minus 3 times something. Similarly, 3 is a 0 of the bottom because we're getting 0 here. So that means x minus 3 is a factor. So you can write this as x minus 3 times something. So you do that, you factor top and bottom, you cancel the x minus 3's, and then take the limit again. If there is no more x minus 3 as a factor, you're not going to get 0 anymore, right? And then you compute, and you will get the result. So as idea, if you have a rational function, and you are in this situation that you get 0 over 0, what you do is factor the top and factor the bottom. If you don't figure out how to factor, like if you cannot say it, because what if you have a higher power here, like a degree 5 or something? That's hard. Like you have to use a bunch of theories from pre-calc. But you already know that 3 is a 0, just divide by x minus 3. Okay? You can do synthetic division. I did a quick example on Friday. Or if you don't remember that, you can use long division if you like. Okay? The remainder will be 0, and the quotient is the other factor that you need. Okay? All right. Anyways, in this case, this is degree 2, so we can factor this, the way that you learned back in high school or college algebra or whenever it was that you first saw factoring. This is just, I would say, the easy ones, right? So the first one, what do we do here? We can just take out an x, right? Common factor x. So the idea here is that we're going to factor, take out an x, and then you get x minus 3. As expected, x minus 3 is a factor. Now this one, anybody remembers how to factor this? How do you factor this? There are 2 ways. There is the AC method, which I would say is easier, but it's a little bit longer. Or if you have practice, you can use the trial and error method, which is quicker. Okay? Let's see. Which one do you want me to remind you? The AC. I would recommend, if you don't remember this, to do AC because it's easier. It's longer, it takes a couple more steps, but it's easy. But it's up to you. I will explain one. Which one do you want me to explain? AC or trial and error?
The second one.
Trial and error?
Yeah.
Okay. So, again, AC you can find it in every book. There is how we do both. Okay. But let me do trial and error. Okay, so here's what you do. Or at least this is how I do it. So the idea is that remember, okay, so you're gonna take this number, I'm gonna split it into 2 numbers whose product is 2, and then I'm gonna take the last number, I'm gonna split it into 2 numbers whose product is negative 3. Okay? That's the first thing that I'm gonna do. In such a way that when I cross multiply and I add, I get the middle value. Okay? So I have, 2 is prime, so there is only one choice there. So I'm gonna do 2x and x. That's the only thing I can do, okay? Of course, I have to have x and x, right? Because the product has to be x squared. So 2, you can only do 2 and 1. And then 3 is also easy. It's only 3 and 1. There are not too many choices there, right? Now, my question is, should I put 3 here and 1 here, or the other way around? 3 here and 1 here, and one of them has to be negative, okay? Because the product has to be negative 3. But I need to do it in such a way so that when I cross multiply and I add, I get negative 5. So for example, if I do this times this and this times this, I'm going to have a 2x, a 3x. One of them will be negative. There is no way I can get negative 5, right? Therefore, I would like to have a 6 and a 1 because I know 6 minus 1 is 5. In this case, 1 minus 6 will give me my negative 5. So I need the 6 negative and the 1 positive. So, this happens in your mind. You're just playing with all of these things in your mind. So I put 3 here and 1 here, and then I need this guy negative. If you cross multiply, you get negative 6x plus x. That's negative 5x. So these guys are your factors, 2x plus 1 and x minus 2. Okay. Also, I guess I did this without having any previous knowledge, but we already know that x minus 3 is a factor, right? So since we have the 2x and x here, then negative 3 better be here. So you can get your x minus 3. Okay? Just figure out what is missing here, and that will be a 1, because that's the only thing that you can multiply with negative 3 to get negative 3. So 2x plus 1, x minus 3. That's how it factors. If you don't remember, if you don't like this, this is quicker and fast, but you need to have practice. You need to have done a bunch of these to be able to do it quick. Okay? If you're not comfortable with this, there is a more general one called the AC method. And basically, here is the idea. You need to look, you have to focus, it's called like this because remember, a quadratic is usually ax squared plus bx plus c, like the general form. Think about the quadratic formula, your a, your b, and your c, yes? So it's called AC method because you look at the product of a times c. The first number times the last number. So what's 2 times negative 3? Negative 6. So we look at 2 times negative 3, which is negative 6. And then here is what you do. You want two numbers whose product is negative 6 and the sum is negative 5. Okay? So I need two numbers with the following condition. Let's call them, I don't know, W1, W2. So I want W1 times W2 to be equal to negative 6. I need the product to be negative 6. But when I add them, I need to get negative 5, which is the middle number here. Can you tell me those two numbers? Negative 6 and positive 1. So these numbers are negative 6 and positive 1. Yes? Now what do you do with those numbers? Well, once you find the numbers, you go here, you take the middle guy, and then you write it as a sum of those two, because the sum equals the middle guy, right? So you write it as a sum. And then you factor by group. So let me do it here. We have 2x squared minus 5x minus 3. Then the first and the last one stays the same. And the middle one, we write it as negative 6x plus x. You see your negative 6 and your 1. Those are the coefficients that we put here. Do you understand this? And now factor by grouping. So now we group the first two and the last two. It will always work. Once you find the numbers, this is going to always work. So in the first group, what can we take as a common factor?
2.
We can take out 2x. So you have x minus 3. And the second group, well, there's nothing to do. We just leave it like that. I'm going to put parentheses just to say that this is the other group. And now among these two, we can see that x minus 3 is a common factor, so we can factor that out. So if you take out an x minus 3, what's left? So the first one, if I take out x minus 3, what do we have left? The 2x. And for that one, if I take it out, what do we have left? The 1. Remember, there's a secret times 1 in here, just so we don't write it. Yes? You can think of this as being times 1. Okay? So when you take out x minus 3, you are left with 2x plus 1. Again, and I guess the other option would be divide. Okay, since I'm here, let me just do everything. If you don't remember this, if you don't remember the AC method, and again, you need to know the division property because what if the power here was 3? Okay, none of the things work. These things is just for degree 2 polynomials. You have a degree 3, degree 4, degree 20 polynomial. How do you factor if you know that x minus 3, that 3 is a 0? So I guess this is alternative 1. This would be alternative 2. Let me give you another one. And that would be the following. X equal 3 is a 0 of 2x squared minus 5x minus 3. So you know that x minus 3 is a factor. Okay? In other words, what this is telling you is that this polynomial, we can write it as x minus 3 times something. Our job is to figure out this something. Okay? So one way to do this is to actually go ahead and take this polynomial and divide it by this. Okay? We know the remainder will be 0, right? Because the division is going to be exact, and whatever the quotient is, that's your result. Okay? That would be the alternative way. And this is, in general, what you should do if you have a degree other than 2 in your polynomial. Because these tricks, they don't work for degree 3 or higher. Do you remember long division? Yes? So I'm going to use synthetic division because it's fastest. Okay? All right, so what you do, you put 3 here. I want to divide by x minus 3. So if you see a negative 3, you put a 3. If it was x plus 3, I put a negative 3 here. Okay? So you put a 3 here, this little box, and then you put the coefficients of the polynomial that you want to divide. So you want to divide 2x squared minus 5x minus 3 by x minus 3. So that's called the dividend, 2x squared minus 5x minus 3. You put the coefficients only. And what's important here is that you have to put, if something is missing, you need to write it. What I mean is, imagine that this guy was not here, the negative 5x was not there, then I would write 2, 0, negative 3. In other words, if this term is missing, that means the coefficient is 0. Do you understand this? All the coefficients have to be there. And then we activate the process. What's the process? Bring the first number down, and then you take this guy, multiply it with this one, put in the next column. You add and repeat until you're done with this statement. So 2 times 3 is 6. We add, we get 1. 1 times 3 is 3. We add, we get 0, and we're done because we don't have more columns. The last number will be your remainder, okay? And these numbers here are the coefficients of your quotient. Now, because we have 2 numbers, that means it's a linear term, x and the constant term, yes? So we can see from here that our qx is 2x plus 1. So then you factor x minus 3 times 2x plus 1. Yes? Again, you learn all of these a while back. Just pick whichever you want to do problems like this. I mean, you should be comfortable factoring, so you should not be looking at this unless you have to. And as I said, that's when the degree is higher. Okay, anyways, the point is that we factor, and as you can see, the responsible for the 0 in the top is this guy. And the responsible for the 0 in the bottom is this factor over here. What we do is that we cancel, and as the theorem that I mentioned on Friday, if 2 functions agree every around, let's say that you're getting close to a certain point. I don't care away from the point, but around the point, if you have 2 functions that are different, but they agree everywhere except at that point, then the limit is going to be the same for both of them. So what we're going to do is we cancel, and we're going to replace this by another function. It's not the same, but it's very similar because away from 3, this function here, this blue function, will give you the same values as this one away from 3. Why they are not the same? Because at 3, this is not defined, this one is. Okay? But that theorem guarantees us that we can do this, and the limit here is going to be the same as this here. Okay? In other words, simplifying is okay. That's what that theorem says. You can simplify when you compute limits. And now, this is straightforward limit. What is this limit? 3 over 7. You just plug in, right? Okay. Okay, you do this in 1 second. I mean, you can do this in less than 20 seconds, right? It's very quick. It took some time because several things that needs to be explained. And you okay with this? Yes? So, rational functions, if you have 0 over 0, factor, simplify, and plug in. That's what you do. All right, so how about number 2? Questions on number 1? Okay, how about number 2? Let's see. So I was limit as x approaches -3 or 1 over x plus 2 plus 1 over x plus 3. What's the first thing that you do when we evaluate limits? Plug in. All right, let's plug in. What do we get? So in the top we get a 0, right? You put a -3 here, and I have -1. 1 over -1 is -1 plus 1, that's 0. Yes? So the top is 0. How about the bottom? It's also 0. So remember, at this point you cannot say anything. This is an indeterminate form, so something needs to be done. I'm just gonna write IF for indeterminate form. Okay? It's an indeterminate form. Let me define the term here. That's what I mean by IF, indeterminate form. Okay, so we need to do something. Now, this one looks slightly different from a previous example because this is not really a rational function. However, what do we do? Let's see, can we turn this into a rational function? Can we turn this into a rational function? Just create denominators, right? Multiply top and bottom by x plus 2, and this is going to become a rational function. This is what we call a complex fraction, right? This is when you have a fraction and you have little fractions inside that fraction. How do you turn that into a single fraction? Just clear all denominators. Do you remember how to do this kind of stuff? I look at your faces and for example, let me do it this so it stays in the notes. Let me do it with numbers first. If you have, let's say, 1 plus 2 over 3 plus 5 over 2 plus 1 over 3. Something like this. It is a fraction that has a bunch of little fractions in it, okay? I want to write this as a single fraction. How do we do this? That's some alternative. You can combine the top and write it as a fraction, right? Add those two fractions, you get a fraction in the top. In the bottom, add those two fractions, you get a fraction in the bottom, and then you divide the two fractions, right? You can do that. Or, but then that requires some steps. Or, in one shot, you can do it. How? Just clear all denominators at once. Find the least common denominator among all the fractions. In other words, the common multiple of all the denominators, and then multiply top and bottom by that, okay? So our denominators are 1, because this is over 1, right? 1, 3, 2, 3. So the 1 doesn't count, so it's 2 and 3. What's the LCD for the common multiple, the minimum common multiple between 2 and 3? 6. So we're going to multiply everything by 6. Yes? You're always allowed to multiply top and bottom by the same number, because that cancels and give you 1, right? So you don't change your fraction. So what you do is multiply everybody by 6. You know, entire top by 6, entire bottom by 6. Let's see what we get. So when you multiply the top by 6, what do we have? 6 plus, now 6 times 2 over 3. The 3 cancel with the 6, giving you 2 times 2 is 4. So we have 6 plus 4. And then in the bottom we have, when you multiply 6 with 5 half, the 2 cancel with the 6, giving you 3 times 5, 15. Plus, and when you multiply the 6 with the 1 over 3, the 3 cancel with the 6, giving you a 2. Times 1, that's 2. Did you understand this? And so this is 10 over 17. And we move on with our life. So here we're going to do exactly the same thing. Just so we don't have numbers, we have variables, but it's the same idea. In this case, there's only one denominator to worry about because everything else is over 1. Yes? So we multiply top and bottom by x plus 2. You okay with this? So everybody gets multiplied by x plus 2. And why am I doing that? Well, because by doing this, I'm gonna turn this into a rational function. Once this becomes rational, I know how to deal with that. If we still have 0 over 0, we do what we did above. Okay? In number 1. Okay, so let's write down what we get. What do we get on top? When we distribute the x plus 2, what do we get on top?
X plus 3.
Okay, so let's do it slowly. So what's the first term?
1.
1, good.
X plus 2.
Plus x plus 2. Everybody understand this? Just distribute, okay? And then in the bottom, there's nothing to cancel, so I'm just gonna leave it as x plus 3 times x plus 2, okay? I'm gonna leave it like that. Okay, so now we combine, and then you see that we have x plus 3 on top, and x plus 3 times x plus 2 in the bottom. The reason why I didn't multiply this denominator is because remember, we want to get rid of that issue. In particular, this 0 is the one that we will need to eliminate. Why? If this was a 3, then my answer would have been 0, right? So this guy is a problem, this 0 down here. And who is responsible for that 0? This x plus 3. So I need to cancel this with something no matter what. Therefore, I don't want to multiply because I want to leave it as a factor, because maybe the hope is that we should be able to cancel this with something from the top. Okay? That's why I didn't FOIL this. And as expected, after we did this, now we have a rational function and an x plus 3 showed up here that we can now nicely simplify. Okay? So we still have 0 over 0, but that problem is gone pretty soon. So as mentioned before, it's okay to simplify. And now we get our limit, which is, what's this limit?
1 over 5.
It's negative.
Negative 1, right? 1 over negative 1 would be negative 1. So in the homework, you have a couple of problems that look like this, okay? I didn't do one like this on Friday, but the idea is pretty similar to the one above. But first, you have to clear denominators. Okay, questions? So if you have rational functions and you get 0 over 0, factor the top, factor the bottom, simplify, then evaluate. If you have a complex fraction like this one, first clear denominators, turn it into a rational function, and then do the previous technique. Factor the top, factor the bottom, and evaluate. Now, let's look at another case, which the class may ask earlier, which is what do you do when you have radicals? For example, something like this. So what's the first thing that we do when we take a limit? Plug in. Just plug in, okay? Don't do anything, because maybe just plugging in, that's all you need, okay? Get a number, you're done. Okay, so we plug in 5. What do we get on top?
0.
So we get 0. Everybody see that? All right, and in the bottom?
0.
0. So, indeterminate form. So something needs to be done. Okay, so what do we do? So here, factoring doesn't do the job, because, I mean, there's nothing to factor. What are we going to factor here? The previous technique doesn't work either. There is no denominator to clear in here, right? So we need to see what to do. Again, ultimately, our goal is to cancel this x minus 5, okay? This guy is responsible for this 0. So we want to get rid of that. But, for example, this radical here is in the way of us being able to do any sort of trick that we can do. Then the idea is, okay, can we at least get rid of this radical, okay? And one way that we can do that is by multiplying by the conjugate. Do you know what the conjugate is? It's just the same thing that you see here, but you change the sign. If it's a minus, you put a plus. If it's a plus, you put a minus, okay? And the idea is because we want to take advantage of the difference of squares property. So when you have a squared minus b squared, what is this equal to? How do you factor this? Say it.
No, it's fine.
A plus B
Uh-huh.
and A minus B.
A plus b times a minus b. Right? That's how you factor difference of squares. We call these guys conjugate expressions. Okay? Notice that they are the same binomial, it's just that one is with a plus, the other one is with a minus. Here your a is the square root of x minus 1, and your b would be 2. Yes? And it has the property that when you multiply an expression like this with its conjugate, what happens? It becomes a difference, but you square both sides, right? And that's exactly what you need, because if you square this, that kills the radical. I want to get rid of that radical. So that's the reason why we use this technique, okay? So if you have 0 over 0 and it looks like this, multiply by the conjugate. This could be on top or it could be in the bottom, doesn't matter. You do the same thing, okay? So the conjugate would be square root of x minus 1 plus 2. But remember, if you multiply on top, you also need to multiply the bottom. All right, so now the numerator becomes, when you multiply these two guys, that's a product of conjugates, so that will be the first guy squared minus the second guy squared. Yes? Over. Now, should I distribute this product in the bottom? Why not?
You're trying to cancel that.
Remember, you want to get rid of this x minus 5, so you want to leave it as a product. Okay? And now we simplify, and the hope is that hopefully, an x minus 5 will show up on top that we can cancel out. But let's see, this square cancels with the radical. So we get here the limit as x approaches 5. So now on top we get x minus 1 minus 4. And indeed, now we can see that the x minus 5 is going to pop up. So combining like terms, we get x minus 5 in the top, which now we are allowed to cancel. And so we get a new limit for another function, but they both coincide everywhere except at 5, so we can replace it. Plugging in, what do we get? 1 over 4. Right? Put 5 here, you have 4, square root of 4 is 2, plus 2, that's 4. So we get a quarter. Okay, questions? Are you okay with this? Okay. All right, so that's what you do. So we have seen, I guess, 3 techniques in this situation. Now let me say how to deal with functions like this. What if you have a piecewise function? Okay, so let me write it here, and let's analyze. So we have number 4. We have the function f of x, and then 2x squared e to the 2x plus 3x plus 1. And we have the 7 here, and here we have tangent minus ln. And my point here is just putting something. Okay, so this is, first one is when x is less than 0. If x is equal to 0, that's a value. And then if x is greater than 0, that's a function. Okay? And then the question is, of course, what happens at 0? Because if I ask you what's the limit as x approaches -5, what pace would you use for this function, for this limit? The first one, because when x is -5, when you're around -5, this is the function that you're looking at, right? You don't care about anything else. Remember, the limit is around the point. You don't care what happens away from the point, yes? So around -5, this is what you look at. If I tell you the limit as x approaches 1, let's say, when you're around 1, but when I say around 1, I mean, 0.999 and 1.01, so you're very close to 1. What formula should you be looking at? The third one, right? You don't care about the other stuff. So those, as you know, this is just evaluated. So of course, the interesting question is, what happens at 0? Because you see, if you are around 0, 0 is the point where the function changes. On one side of 0, we have this formula. At 0, we have this value. And on the other side of 0, we have this other formula. So 0 is a troublesome point. Do you understand this? So we want to analyze that. So the question is, what is the limit as x approaches 0 of a function? So how do we do this? Yes?
We compute the size of this,
Very good. Why?
because
Good. So, first thing is that you need a formula. If you want to compute this limit, you need a formula to look at to be able to evaluate the limit, right? Now, the point is that you have, let's see, we see 3 formulas here, but really, how many formulas do we care about? Do we care about that 7? Why not?
Because we don't care about what happens at 0.
Very good. We don't care about the value of the function at the point, right? At 0, the function can be doing whatever it wants. It may not even be defined. I don't care, okay? We care about around the point. So, around 0, there are 2 possible formulas, right? The first one is where? To the left or to the right of 0? To the left, because x is less than 0. Yes? And the second formula? To the right. So when you get close to 0, now we need to see how we're getting close to 0. From the right or from the left? Because depending how you're getting close to 0, that's the formula that you need to use. So this question, even though it didn't ask you for it, you naturally need to consider side limits. Right? And remember, why side limits? Because if we compute the 2 side limits, what do we need? What do we need to happen for both of them?
They have to be the same.
They better be the same. If they are the same, then this limit will exist and will be equal to whatever that value is, right? If the side limits happen to exist, but if they are different, that means you're going to have a gap in your function, so the limit doesn't exist. This one, as x approaches the point as a whole, see? Okay? We talked about that on Wednesday. Remember, this limit exists if and only if the side limits both match, exist, and they have to be equal to each other. So for this question, this actually needs, so this needs side limits. So typically when you have a piecewise function and the limit that you are taking is at the point where the function changes formula, you need to do side limits, okay? Because you have to pick a formula to work with. And you don't know that until you know on what side you are. Okay, so let's do it. So the side limit would be, first let's do it from the left. And then we're going to do it from the right. Okay, so remember, when you take a left limit like this, when you see this, this means x approaches 0 from the left. So what do you know about x with respect to 0? How do they compare? Is it bigger or smaller than 0? So this just means that x is less than 0, right? So that's your clue to know what piece to pick from your function, okay? You're approaching from the left, so x is less than 0. Let's go to our function. What's our formula when x is less than 0? What's our formula? The first one, right? So that's the formula we're going to use. So this is the limit as x approaches 0 from the left of e to the 2x plus 3x plus 1. Everybody okay with this? Okay. Now we compute. What's the first thing that we do when we evaluate a limit? Plug in. So in this case, we can plug in. Remember, the limit of the sum is the sum of the limits. So this is just these 3 limits, and for each of them, these are exponential, polynomial. So just plug in. Okay. So that would be e to the 2 times 0 plus 3 times 0 plus 1. So what do we get here?
2.
We get 1 plus 1, which is 2. Yes? All right. So the left limit equals 2. We cannot claim victory yet. Okay? We need to compute the right limit and see what we get. We better get 2. If we don't get 2, that means the limit does not exist. The original question, the answer will be does not exist because the side limits will differ. Okay? So we better get 2 here if we want to answer that this exists and equals 2. All right. So again, similarly, because x approaches 0 from the right, what do we know about x? So it's greater than 0, right? So this tells you what formula to pick. Now that means that we should be looking at the third formula. Yes? So this is the limit as x approaches 0 from the right, and then we have tangent minus ln of x squared plus 1 plus 2 or cosine. Again, first thing that you need to do is plug in because it's just as easy as just plugging in. So, and indeed, here just plugging and then that's it. So again, it's a fraction. Remember, plugging in the top, plugging in the bottom, and then we just plug into each of those functions. So we're gonna have tangent of 0 minus ln of 1 plus 2 over cosine of 0. What's tangent of 0? It's 0. Good. So this is just a 0. What's cosine of 0? That's 1. And what's ln of 1? 0. So this becomes 0 minus 0 plus 2 over 1. So the final answer is 2. Yes? So, okay, let me just keep it like that. So the right limit is equal to 2. The left limit is equal to 2. Do they match? So what can we say about the original limit? It exists and equals 2. Yes? If I would have done a plus 3 here, for example, in the problem, if I would have put plus 3, what would have been the answer? It would be 3 here. So what would you say about this? Does not exist. Because the left was 2 and the right would have been 3. Do you understand this? So, really, I could have changed this over 1 to get whatever outcome I want in this problem. Okay? But it better be 2. So a typical question is, for example, I could have put it like this. Probably should have done that. I could have given you this function where a is a constant but it's to be found. Okay? You don't know what a is. And then the question would be, what should be a so that this limit exists? The limit as x approaches 0. So find the value of a that will make the limit as x approaches 0 exist. What do? What we just did. The left one has nothing to do with a, so the left limit will give you 2. Yes? So that means if you want the limit to exist, we better get 2 in the right limit. You compute the right limit, there will be an a here instead of a plus 2, right? But that's just a number. So when you compute your limit, what would you get here? No, there was an a here. So what would you get here? Just a. Now at that point you say, okay, I want the limit to exist. So what must a be equal to? It better be 2 because this limit better be equal to 2 if you want the limit to exist. And that will be your answer. Okay? You're gonna get questions like this. In the next chapter, when we talk about derivatives, there will be questions like this. I give you a function, and then there's a constant that is unknown. Find the value that will make the derivative, the function differentiable at a given point. And this is the kind of things that you have to play. Okay? All right. But here, just like that. So, the point is that the limit, the left limit, agrees with the right limit. They both equal 2. So the actual limit that we are interested in exists and equals 2. Okay? All right. Questions?
I have a question.
Yes.
So it's like when we see that we're not given an equation and we have multiple to choose from, we know we have to compute the side limits to find out if the whole limit exists.
Depending what you're approaching to. So for example, if it would have been x approaches -3,
Then you use the first.
you just use the first one and you don't have to worry about that. It's just when you approach the point that makes the function change formula. Okay? That point at which the function changes formula, that's the one that you have to worry about. Because around the point, the function behaves differently. And you have to see what happens. Okay? And typically, if you see a piecewise function, the interesting question is what happened at that point where the function changes formula. Okay, does it break or it doesn't break? Like in this case, this means that whatever the picture is to the left, then to the right of 0, it connects right there. Okay. Now, as you know, let's see. If you were going to graph this function, remember, eventually we want to graph function. If you were going to graph this function, what's going to happen around 0? How would that look like, more or less? Are we going to have a hole or not? Let's see. When x is 0, the y value of the first piece is 2, right? And the y value of the third piece is 2. So we have the point 0, 2. Yes. What happens at that point? Do we have a hole? Yes. Why?
It's actually 7.
The function is actually 7. So what's going to happen is that the left part is going to be doing something, then the last part is doing something else, which is going to match a 0, 2 with the first part. But at that point, we need to have a little hole because the function itself is 7. That's it. Okay? That's the middle piece. Again, the limit doesn't care about that, but if you want to graph the function, you need to care about everything, right? So at that point, we have a hole. The point is 0, 2, because at 2, the value will be 7. So we're going to be putting all of these ideas together later when we start graphing, but that will be towards the end. Okay, and then let me do this one. So this is absolute value of x minus 2 over x minus 2. And this is the limit as x approaches 2. What's the first thing that we do? Plug in. Okay, when you plug in, what do we get?
0.
So we get 0 on top, and on the bottom, 0. So we get 0 over 0. So this is an indeterminate form. So we need to do something about this. What do we do? Again, there's nothing to factor, right? There's no conjugate trick here that will do the job for us. There's no clearing denominators. What do we do? Here is the idea. Is this let's see, is this a piecewise function? Claim that it is. The absolute value is a nice little function that's actually piecewise. How do you define the absolute value? So recall. How do you define absolute value? What's absolute value of x? Who can tell me?
X positive.
Or negative.
Plus or minus.
Just positive x.
What did you say?
Positive x. Sorry, just x.
So absolute value of negative 2 would be negative 2.
No,
Okay. Okay, I ain't computer. If you tell me absolute value of x is x, then I look at it and say, oh, absolute value of negative 2 is negative 2. Because x means what's inside, right? So how do you define? Let's say that you want to tell a computer what absolute value is. How would you do it? Okay, but the computer cannot compute distance, right? So we need an actual formula, like the calculator. If you want to tell the calculator, you want to program the absolute value function in your calculator. It doesn't go and measure distance, right? So that's the meaning. Good. But how do we actually compute absolute value? You don't go around measuring distance from 0, right, to compute it. So what do you do in practice?
It's a piecewise function.
What do you do? What do you do in your brain? Let's see. What is absolute value of 2?
2.
What's absolute value of negative 2?
2.
What did you do?
So if x is negative, then it's the opposite, and if it's positive, it's just the x.
You see, you are asking yourself a question. When you see absolute value, even though you don't, you think that you're not doing it, you are doing it, right? You are in your brain. You're saying, okay, is the stuff positive or negative? If it's positive, I leave it alone. If it's negative, what do?
It's the opposite.
You change the sign, right? You're doing that. Maybe you don't want to admit it, but you're asking that question yourself, okay? So when you see absolute value, you need to ask yourself the question. Whether x is positive, let's include 0 in there, because, 0 doesn't matter, it will just be 0, or negative, and depending what it is what you do. So in the first outcome, if x is greater or equal than 0, what do? It's the same, you don't do anything, right? So it's just x. And if x is negative, what do?
X times negative 1.
Very good. You change the sign. Remember, what operation do you do to change the sign? You multiply it by negative 1, right? So that will be negative x. In other words, when you told me absolute value of negative 2 is 2, really what's going on is that you're doing minus minus 2, right? To make it positive 2. That's the operation that you can do to make a negative number positive. Okay, so the absolute value is just a nice little function that in reality is piecewise. Okay, it's piecewise. So it's a function x as long as x is greater or equal than 0, and it's a function negative x if x is less than 0, right? So when you see an absolute value function, you need to understand that there is a piecewise behavior here. For this one, the point at which it changes formula, right, is 0. But our function is x minus absolute value of x minus 2. That will be this one shifted to the right 2 units, right? So the role of 0 here is played by what in here? By 2, right? 2 is the point at which this top changes formula. So we need to analyze what? Should we do side limits or not?
Yes.
Yes, because we need to know which one of the two formulas we need to use. Is it x minus 2 or is it negative x minus 2? Do you understand what I'm saying? Okay. So, moral of the story, if you see something like this and you see the absolute value, if you get 0 over 0 and you see absolute value, you need to understand the side limits are in order also. And here is the reason why. Because we would like to just cancel these guys, okay? Why not? But the thing is that we have to be careful because, this could be, when this is positive, then you cancel, you're going to get 1. But when this is negative, when you cancel, you're going to get negative 1. Because the top is always positive. In other words, if this is your absolute value of x, what is this? This is 1 if x is greater than 0, and it will be negative 1 if x is less than 0. Do you understand this? Right? Like absolute value of negative 2 over negative 2. What is this? That's negative 1, right? Because it's 2 over negative 2. So, whenever, and this is a similar situation what we have above. So this is 1 when x is positive, and it's negative 1 when x is negative. This time we don't include 0 because at 0 this is undefined. Okay? So something like that is happening here. Okay? It's just that this problem is being translated to 2 instead of 0, but the same sort of outcome is going to happen. Okay, anyway, so the point is that we need side limits. This is going to come up again when we talk about derivatives, okay? All right, so if we want to analyze the limit as x approaches 2, we're going to do it from the left. And then we're going to do it from the right. Okay? Now remember, and the idea here is that we want to get rid of the absolute value. And if you want to get rid of the absolute value, this here is telling you the recipe. You can get rid of the absolute value as long as you know what's the sign of the stuff that is inside. If the stuff that is inside is positive, eliminate the absolute value without doing anything. If the stuff that is inside is negative, you can get rid of the absolute value, but you need to pay a price. What is it? Multiply by negative 1. Okay? So if we want to get rid of this absolute value, we need to know the sign of x minus 2. Yes? Is it positive or is it negative? So we can get rid of it. Okay, and this right here is going to tell us. So because we're approaching 2 from the left, what does this mean about x? Is it less than or greater than 2?
Yes.
X is less than 2. So if we move the 2 to the other side, because we want to analyze x minus 2, right? So this means that x minus 2 is what? Is it less than or greater than 0? It will be less than 0, right? Just subtract 2 over here and you get x minus 2 less than 0. Do you understand this? So to the left of 2, x minus 2 is negative. So if I get rid of the absolute value, what's going to happen? What do I need to do? I want to write x minus 2 without absolute value. So what do I need to do? Can I just say this? Or do I need to do something about it? What's the rule? If the stuff inside is negative, what do you do when you get rid of the absolute value? Put a minus in front. Do you understand this? Yes? And then the bottom stays like that. Remember, we're putting the minus in front so we can make it positive, because to the left of 2, this is negative. You need to make it positive because that's the value, so that's why we're putting this minus, right? Remember, here this is like 1.9. 1.9 minus 2 is negative 0.1. But you want to have positive 0.1. You don't want to have negative 0.1, so we need to put the minus to make it positive. Yes? So now we can cancel, so we get limit as x approaches 2 from the left of negative 1. And what is this limit? Negative 1. Remember, the limit of a constant is a constant. Did you understand this? Now what's going to happen from the right? What do we know about x here?
Greater than 2.
This means x is greater than 2. So what can we say about x minus 2?
Greater than 0.
It's positive. Remember, we are interested in what about this guy, x minus 2. Okay? You need to know something about x, and then you can tell me something about x minus 2. Okay, so x minus 2 is positive in this case, so that means Can we remove the absolute value without doing any changes? Yes, because the stuff is positive anyways. So there's no need for an absolute value. And so now this becomes just 1. And what is its limit? 1. Okay, so these are our side limits. So now what can we say to our question? What can we say about the limit as x approaches 2? It does not exist. Why?
Because the side limits are different.
Side limits are different, right? So these guys are distinct. They're not equal to each other. Yes? So the limit as x approaches 2 does not exist. So side limits are different. There is a gap. The way this function looks is like this. This function is how it looks. So, it's that piecewise, but shifted to the right at 2. Instead of a 0, the split happens at 2. So, to the left of 2 is going to be -1, the function -1. And then to the right of 2 is going to be the function 1. And then, that's it. Open circle on both because it's not defined at 2. That's the graph of the function. So when you approach from the left, you get -1. When you approach from the right, you get +1. The limit does not exist because the side limit is don't match. Okay? All right. Questions? You okay with this? So again, we are seeing several techniques, okay? Depending on how the function looks is the approach that you take. Notice that all of these cases were 0/0. But the way that we dealt with them was completely different. It really depends on the function that you have in front of you. Okay? And you know some techniques. If it's rational, you know what to do. If it has radicals, you know what to do. If you see absolute values, well, it's really piecewise, so you need to do side limits. Okay? All right. Are we okay? Okay, so was that. Okay, so let's see. It took longer than I wanted on that. Okay, that's why I said that you cannot rely too much on the scale that I that I gave you because things don't go as planned as usual. That's fine. I don't want to rush things because if we rush, then you don't understand and there is no point. Okay, so now that we have an idea about limits at a point, then notice that in all the cases that we have seen, either the limit did not exist or we were getting a number as a result. Okay? But what if when you take the limit, let's say it still does not exist because the function doesn't get close to any number, but you actually see that your values keep growing and growing bigger and bigger and bigger non-stop. Okay? In that situation, the limit does not exist, but we say that the limit is infinite. Okay? So we call these infinite limits. And the reason why they're important is because those are the ones that allow you to figure out vertical asymptotes for functions. Okay? You know what a vertical asymptote is, right? It's a vertical line that you cannot touch, but the function gets very close to it non-stop. So the definition is that around this line, the function goes to either positive or negative infinity. Okay? If you look at the graph. All right. So let's talk about this. You already have some idea from college algebra and pre-cal, so this should not be too much of an issue. So let's see. Let's start with an example. So consider the function f of x equals 1/x minus 2. And what do you think is the point that we should be analyzing here? What value of x should we analyze? 2, right? Because anything other than 2, this is a perfectly fine function. When you take the limit, you just plug in, right? So another question is, what happens when we are close to 2? We cannot plug in 2 because the function is not defined at 2, right? But what if you get very close to it? What's going to happen to the function? So that's the question that we're going to ask. So the question is, I'd like to know, I cannot plug in 2, but I can get close to it. So let's do it from the left. And let's do it from the right. Okay? So remember, when we write this, there's a question that we are asking here. What is this question? Is this function 1 over x minus 2 getting closer and closer to some value whenever x is very close to 2 from the left, where number is less than 1? That's the question that we are asking. Okay? And similarly, the other one, but we're getting close to 2 from the right. So let's see. What do you think? What can we say about the first one? What happens when we get close to 2? What happens to the denominator? Yes? Okay, but let's look it down so everybody can understand. So what happens to the denominator when we get close to 2?
It's getting bigger, the fraction increases.
The denominator. What happens to the denominator, the bottom? It gets very small, right? It approaches 0, right? And what happens when you have a fraction in which the top is fixed, in this case is the number 1, and you are dividing this consistently by smaller and smaller and smaller numbers? What happens to the overall value of the function? It gets bigger. Now here we have to be careful. We need to see what type of numbers are we dividing by. Are we dividing by positive or negative numbers? Because if you divide by negative number, then it's actually getting smaller, right? Because it's going down. In absolute value, it's getting bigger, but it's really going down because you're getting negative values. You understand this? If you divide by very small positive numbers, then yes, it goes up, positive. You understand this? So we see that the top is a 1, the bottom goes to 0. Every time that you see that, then you know that your function is going to be unbounded. Either goes up non-stop or down non-stop. Okay, unbounded means it doesn't stop. It keeps growing to positive infinity or going down to negative infinity. Okay, so in this case, which one is it? So for the first one, limit as x approaches 2 from the left of 1 over x minus 2. What can we say here? So again, x is less than 2, right? So what do you know about x minus 2? Is less than 0. So this bottom here is approaching 0, but it's approaching 0 from the left, right? In other words, this is getting very close to 0 with negative numbers like negative 0.1, negative 0.01, negative 0.001, etc. But with negative numbers, right? So what do you get here? Negative 10, negative 100, negative 1,000, negative 1,000,000, and so on and so forth. Yes? So the closer you are to 0 from the left, then this fraction is going to be getting smaller and smaller. So in absolute value, it gets bigger and bigger. But the thing is that we're dealing with negative numbers now. Do you understand? Positive divided by negative. So the bottom gets close to 0, the top gets close to 1. So whenever you see something like this, this has the shape of number over 0. Whenever you take a limit, if it looks like this, in which this number is not 0, because remember, 0 over 0 is a different story. But if this number is not 0, if this is not 0, then this limit is either positive infinity or negative infinity. Okay? We just need to decide which one is it. And how do we decide which one is it? We need to see, okay, what's the sign of this number, which in this case is positive, right? And then, yes, you're approaching 0, but how? Are you approaching 0 with positive numbers, or are you approaching 0 with negative values? Because depending how you do it, the overall sign will tell you which one of the two is. Okay? Now, don't get me wrong. This still means that the limit does not exist. But there is a further information here. This is different from the gap example. Okay? Here it does not exist because the function keeps going non-stop. So instead of saying it does not exist, what we say is positive infinity, or in this case, is negative infinity. Okay? So in this case, we say that the limit does not exist. Let me say this: does not exist since the values of 1 over x minus 2 keep getting smaller and smaller. Let me specify in the negative direction, because if I say this, then you may start thinking about getting close to 0, and it's not 0, it keeps going down to negative. In the negative direction. So keep getting smaller and smaller without bounds. Okay, that's what happens. That's why the limit does not exist. Instead of writing this every single time, we say, okay, this we write it as negative infinity. Okay? So we write that the limit as x approaches 2 from the left of this function will be negative infinity. But you need to understand that when we write this, what we're saying is that this function, the values are getting smaller and smaller without bound in the negative direction when you get close to 2 from the left. Because we want to write this integers every single time, so we use the signal. But understand that this means that the limit does not exist, okay? So if the question is, does the limit exist? Your answer has to be no, it does not exist, okay? But if they ask you find the limit, instead of saying d and e, you will write negative infinity, okay? And typically, for example, in the homework, the problem will tell you, if it's infinity, you write infinity or d and e, if it's not infinity, okay? Okay, did you understand this? And how about the other one? Limit as x approaches 2 from the right of 1 over x minus 2. We would write positive infinity. Why? Again, the bottom approaches 0, the top approaches 1, but this time we're getting close to 0 with positive numbers, so values are going up non-stop. Yes? So, okay, so I don't want to. Should I write the same sentence? Because technically, I should write the same sentence and then tell you how you write positive infinity. But do you understand? Okay, I'm just gonna say this is equal to positive infinity, and just say nope. This is as above. It means the limit does not exist, but the function is unbound. It's unbounded, but this time is in the positive direction. In the positive direction. Okay. So that's what we call an infinite limit. Okay. So let me write down the definition. I'm not gonna give you the formal definition because we haven't talked about epsilons and deltas, and we don't really need it for what we're gonna do. But this is really the analysis that we do. So, what's the behavior of the function when x gets close to this number? If we see that it grows up without bound, then we say positive infinity. If it goes down without bounds, we say it's negative infinity. So definition, let f be a function and a be a number. Then number 1, limit as x approaches a of f of x equals positive infinity. Whenever we write this, it means that the values of the function are growing bigger and bigger without bounds whenever x is very close to a. Now here I'm doing it from either side, okay? Of course, the same thing will be if it's side limits, okay? But I'm just going to write this one, and then the same definition applies if it's from the right or from the left. So this means that the values of the function, the values of f, grow bigger and bigger without bounds as x approaches a. And then similarly, if the limit as x approaches a of f of x, whenever we write negative infinity, it means that the values of f decrease without bound without bounds. So in the negative direction, okay, negative direction, as x approaches a. And the remark is that the same definition applies for side limits. So same idea for side limits. Okay? So the way that usually these sort of infinite limits, we call these infinite limits because the answer is infinity. And the way that they normally come up to be is, as I mentioned earlier, when you take a limit of a function and the top is a number that's not 0, and the bottom is 0. When you have a number divided by 0, it's going to be either positive or negative infinity. Or maybe does not exist. For example, if the question would have been here, what's the limit of 1 over x minus 2 as x approaches 2? What would be the answer? Here was from the left, here is from the right. What if I just say x approaches 2? Why? It goes to different places, right? To the right, it goes to positive. So to the right, it goes to positive infinity. To the left, it goes to negative infinity. So around 2, the behavior is different, right? If it would have been 1 over x minus 2 squared, if I would have squared x minus 2, what's going to happen? It will go to positive infinity on both sides. Yes, because a function is always positive. Do you understand this? In that case, we would say the limit is positive infinity as x approaches 2. Okay? So you have to see the behavior around the point. You know it's either positive or negative infinity, but it could be it does not exist if you're not taking aside limits, and then the infinities that you get are different. Okay? And to decide which ones are they, you have to analyze the sign, as we did here. Okay? Here x minus 2 was negative, and here x minus 2 is positive. Okay? Let me write it here. I didn't write it. Remember, this means x is bigger than 2, so x minus 2 is positive. Okay? So you're getting positive numbers here all the time. That's why it's positive. Are we okay? All right, so let's do some examples, and then we're going to define vertical asymptotes. Before we do examples, let me write down the properties. So properties of infinite limits. Let's see. Let's see. Oh, it's called A. We're calling it A. Let A, L be real numbers. F, G be functions such that. So whenever I want to write such that, I'm going to write ST. Okay? So such that. So let me just say this means such that. Okay? Okay, so such that, and then let's say that the limit as x approaches a of f, let's say that f is a function whose limit is infinity. Okay, so I'm going to write infinity. If we write infinity, it really means positive infinity, but everything I'm saying here also applies to negative infinity. It's just that I don't want to write the same property 2 times. Okay, so when I say infinity, it could be positive or negative infinity. Okay, for the sake of okay, and let's say that the limit of the function g is just a value. That number L. So we have 2 functions, and we have this point A and F. When you get close to A, the value of the function, the value of the limit is infinity, so F is unbounded, and G approaches the number L. Yes, that's the situation. Okay, so let's see. The natural question is, what will be the limit if we look at the sum of these 2 functions? So what's the limit as x approaches A of F plus G or minus G? What do you think is the answer? Here, technically, we cannot write this as a sum of 2 limits, okay? Because that you need the limits to exist, both of them. And here, this one doesn't exist, because remember, infinity means it does not exist, okay? So you technically cannot split. But still, remember, the question is, what happens to this function? Let's look at the plus. What happens to this function, f plus g, when x is close to a? Let's see, what happens to f? It goes to infinity. It goes very big. What happens to g? It goes to L. So the question is, what's infinity plus a number? So something very big plus a number. I don't care what L is. It could be positive, it could be negative, it doesn't matter. You have here something very big plus a number. What's the answer? It's big, right? If you are a millionaire and then you need to pay $100, does it really matter whether you pay the $100 or not? You're still a millionaire. Unless you have 1 million and now you have less than $1 million, you pay $100. Right? The point is that when you have a very big number, you can add or subtract. When you have something that's growing very big non-stop, if you add or subtract something that's fixed, that's not going to change the behavior of this function. Yes? So this is still infinity. So the infinity wins over the number. Do you understand this? So this would be infinity. Now, here, of course, you have to take this with a grain of salt in the following sense. I mean, it's infinity, but let's see, here it will be whatever this infinity is, right? Because the sign of G is not going to affect the infinity. But if it would have been the other way around, let's say if I say G minus F, you take the limit, right? Now we have a number minus infinity, right? Now here several things matters. If the L here is positive, right? If G gets close to a positive number and F goes to positive infinity, what will be this difference? Negative infinity, right? Because 5 minus a million is going to be a negative number, yes? So the answer will be negative infinity. Now, if this approaches negative 3, so if L is negative, what will be the answer here? Negative infinity as well, because you will be subtracting, right? And when you subtract negative minus a number that's positive, then when you subtract, you use negative infinity. So the point is that you have to see, you know, the order, which one is first and which one is second. Is it the number or is it the infinity? And are you adding or subtracting? There may be a slight change in the sign of the infinity that you have. But the point is that if one of the functions is infinity, your answer will also be infinity. Okay? Which one is it? Is it positive or negative? You have to see the situation that you are in. Okay? That's what this property is telling us. Okay, so hopefully that's clear. How about the product? What do you think about it? So what is this product? It's the same idea. When you get close to A, this what happens to this product? Well, this is very big, right? This approaches a number. What would this product approach to? So that would be infinity. Okay, so there is a slight thing that we have to be careful about here. What if this number is 0? What if L is 0? In other words, this is something very big times something that's getting very small. That's another indeterminate form. We're going to deal with that later. 0 times infinity, we don't know. It depends which one is growing faster. So is the infinity faster than the 0 or the other way around? Okay? You're going to see what I mean later. So unless the L is 0, if L is just a number different than 0, then this will be either positive or negative infinity depending on the sign of L. Okay? So I guess I am forced to write this. So if L is positive, if L is a positive number, so the limit of G is positive, then this is just whatever infinity F has. If S, in our example, we said that F was positive infinity, so it would be positive infinity. But if this was a negative infinity, this would be a negative infinity. Do you understand this? It keeps its sign. But then, if your L is negative, we flip the infinity, right? Because we have to change the sign. Now, I want you to understand that, let me just say here that if L is 0, then we are in the presence of another indeterminate form. We will discuss how to deal with this after we talk about derivative. One of the applications of derivative, we're going to understand how to deal with this case. 0 times infinity. Okay? For now, you know, this is the 0 times infinity situation. Or, you know, that's it. This is the infinity times 0 situation. That's an indeterminate form. Okay, so in that case, if this happens at this point, you say, well, I don't know. You need to teach me more. Okay? Because what we have, we cannot do anything yet. Okay, are we okay with this? All right, so that's that. And how about the quotient? So, what if you have G over F? What is this? In other words, this is the case in which the top is a number, right? Because the limit of the top is a number, L, and the bottom is something that's going to infinity. It doesn't matter if it's positive or negative. So what happens to this quotient? What happens when you have a number and you divide that, a fixed number, and you divide that by something that gets consistently bigger and bigger and bigger? What happens to the whole thing?
It's smaller.
It gets very small. Small to what? Towards what?
Negative 3.
You sure?
0.
To 0. Remember, the top is a fixed number, and you are consistently dividing this by something bigger and bigger and bigger and bigger. What are you getting? Very small numbers, close to zero. Now, if it's positive infinity, you get close to zero from the top, with positive numbers. If it's negative infinity in the bottom, you get close to zero from below. But still, you're going towards zero. Okay? So number divided by infinity in the limit, that's zero. That's another property. Okay? And remember, a number divided by something approaching zero, that will give you infinity. Yes? But the other way around, a number divided by infinity, that is zero. Okay. Are we okay with this? All right. So, for example, think about the function 1 over x. It looks like this, right? So, this is 1 over x. When you get close to zero, what happens? Let's say from the right, what happens to the function? It goes to positive infinity. But what happens when x approaches infinity? When the bottom approaches infinity? What happens to the function? Look at the graph. What's the function doing when x approaches infinity? It goes to zero. So if the denominator is infinity, then the limit is zero. Yes? We will talk about limits at infinity next, because this concept is infinite limits. Limits at infinity is why do we put an infinity here? Because right now we have been putting numbers here all the time. Yes? But you can put an infinity here. In other words, what's the function doing when x is very big? That's the end behavior of the function. You did that in pre-calc when you were analyzing polynomials and rational functions. Okay? But that's the next topic. Okay, so that's that. So with these little properties, then we can do some examples. Where are my examples? Here. So examples, find the limit. If possible, of course, if they exist. So let's do limit as x approaches zero of 1 plus 1 over x squared. And let's do the same one, but let's do 1 plus 1 over x. And let's do limit as x approaches 1 from the left of x squared plus 1 over cotangent of pi x. All right, let's do this trick. Actually, start working on it. I'm gonna take attendance. So give it a try, and then we'll discuss. Just want to make sure that we're up to date with everything. Okay, the first one. What do we get? Yes. The positive or negative? Very good. Does everybody see that this is positive infinity? No? Okay, why not? What's the problem?
I don't know, like, the steps. Like, I was trying and then I just got stuck. So.
There is no steps. You just have to analyze. Just think about, look at the definition here. You know, this is just a question that we're asking. When you take the limit, you know, if it happens that the function grows bigger and bigger, then we say it's infinity. If it grows smaller and smaller, then we say it's negative infinity, in the negative direction. Yes? So in this case, why would we think about infinity? Well, you see a sum. What's the first thing that you always do? You plug in. If you plug in, what do you encounter? A 1 over 0. What happens when you have a number over 0? You need to know this. When you have a number over 0, that's infinity. Right? Now, your job is to analyze what type of infinity is it. Is it positive infinity? Is it negative infinity? Or maybe it's different behavior on both sides, so it will not exist eventually. You know, then you need to start analyzing the function. Yes? But the first thing is you plug in. If you get a number divided by 0, a number different than 0, okay? Then that's infinity. And we say it right here, right? And the top is a 1. This is 1, so I don't care about this. This guy is just 1 plus whatever we get here. Yes? This is a 1. The bottom is 0. I know this 1 over x squared is going to give me some sort of infinity. Which one is it? Well, because it's x squared, it doesn't matter how you approach 0. This is always positive, right? So this is going to go to positive infinity. So positive infinity plus 1 is just positive infinity. Do you understand this? There is no calculation to do. It's just analyzing. Yes? Okay. So Thing is that this guy went to positive infinity, and when you do positive infinity plus 1, that's just infinity. Okay. How about number 2?
Does not exist.
Why?
What's the difference on both sides? One's negative infinity, the other one's positive.
Very good. You see, so this one is just like the first one, just like instead of x squared, we have an x. So still we have a 1 over 0 here, right? It's going to give you infinity, but which one is it? Well, now it matters because the sign of this function depends on how you're approaching 0, right? If you do it from the left, this will be negative, therefore this is going to go to negative infinity. If you do it from the right, it's going to go to positive infinity. Also think about the function, it does this, right? Well, it does this, the 1 over x. So at 0, the limit does not exist. So this does not exist. Do you understand this? So maybe here I should write something. So let's see. Right does not exist. And I would say, well, this time from the left, notice that here this is going to be negative infinity since x is less than 0 and 1 over x approaches negative infinity as x approaches 0. Yes? This is an alternative way that we write limits. Okay? Here I'm saying this function approaches negative infinity whenever x is close to 0. Okay? Just not writing the limit. So because x is negative, then we have that this part here is a negative infinity. So 1 plus negative infinity is still negative infinity. Yes? And then similarly, from the right, this one is going to be positive infinity, since in this case our x is positive and 1 over x will grow without bound when you get close to 0 from the right. So that's why it's positive infinity. So around 0 the behavior is different, so it does not exist. I mean, even if it would have been infinity, it still would say, it does not exist, but there is meaning to it, right? Here we're saying it does not exist because the behavior is different. Here it also did not exist, but we know the function is going on both sides. Okay? All right. So, just be careful because if it's not a side limit, then having a number over 0 not necessarily means immediately that you get infinity. It could be does not exist. Okay? But you have to be analyzing infinity cases. That's the point. That's the clue. Are we okay? Number 2? Okay. How about number 3? What happens when we, remember, what's the first thing that you do? Plug in. So what happens when we plug in? So what do we get on top? What do we get on top? So we get a 2, right? What do we get in the bottom? You get cotangent of pi. What do you know about cotangent of pi? Remember, cotangent is cosine over sine. Right? Cotangent is cosine over sine. Now, what's sine of pi? So cosine of sine. So cosine of pi over sine of pi. Let me write it here. So this is cotangent of pi, right? But what's cotangent of pi? So remember, cotangent is cosine over sine. Yes? Okay, and what's cosine of pi? -1. Remember that. We talk about the unit circle on Wednesday, right? So pi is over here. I mean, you think about the unit circle, pi is over here, 180 degrees. So the point corresponding to it is -1,0, right? The x gives you the cosine, the y gives you the sine. So cosine of pi is -1, and sine of pi is 0. Yes? So what would this be? What is this? And remember, really, cotangent of pi is not defined because you cannot divide by 0, right? But we're taking limits, really. So x is not really -1. X is not really 1. We're getting close to 1. Yes? Remember, this is a limit. So I should write here. Let me write an arrow here for a second. So we get cotangent of pi, and we're trying to analyze what happens to cotangent of pi. So and remember, this just means that we're getting close to pi because itself cotangent of pi we know is undefined. This is undefined. But the question is, what if you get close to pi? Okay. Okay, so if you get close to pi, in this case, we're gonna do it from the left because x is less than 1, so this is less than pi. So we're getting close to pi from the left, okay? But the point is that the top goes to -1, the bottom is gonna go to 0, so a number over 0, what would this be? Well, some sort of infinity. It could be positive, could be negative, we don't know, okay? It could be positive or negative, but let me write here positive or negative infinity. Do we really need to dive deeper and see which one is it? Do we really care about it? Well, no, because the actual problem has a 2 on top and an infinity in the bottom. What happens when you do 2 divided by an infinity? It goes to 0, regardless of positive or negative. So I'm not going to actually dive and try to see if it's positive or negative infinity. We can do it, but there's no need to. We just know that this is some infinity here, right? And then the original problem has a number on top, some infinity in the bottom, the answer will be 0. Yes? So this is going to be, we're going to figure it out now, but let me just put it like this. Once you see this, you already know that this will be 0. Okay? Let's figure out which one is it. Let's see. At the top, when you get close to pi, for cotangent, when you get close to pi, the top gets close to -1. Yes? Because cosine of pi is -1. How about the bottom? So we're getting close to pi. How? Because 1 here is approaching from, because x is approaching 1 from the left, that means x is less than 1. So this argument is approaching pi from the left because you're multiplying by pi by a number less than 1, 0 point something. You understand this? So here we're doing it from the left. So I would like to, okay, let me rewrite this and write as a limit. So really the question is, and let me change the as theta approaches pi from the left of cotangent of theta. Let's write it like that. So now we know that this is the limit as theta approaches pi from the left of cosine over sine okay? And then we know that the top goes to -1 because when you get close to pi, regardless of the side, this is gonna go to -1 and the bottom goes to 0. So that's a -1 over 0, so we know this is either positive or negative infinity, okay? We wanna know which one is it. And for that, we need the sign. We need to know, okay, the top is a negative. Now, here you get close to 0, but how? With positive or with negative values? So here, and for that, you need to know the quadrant of theta, right? Because if you want to know the sign of theta, whether it's positive or negative, you need to know the quadrant of the angle. So what do you know about theta here? So focus here. What do you know about theta? Is it bigger or less than pi? What is it? Less than pi. We're approaching from the left, right? So theta is less than pi. What quadrant is this? This is quadrant 2, right? Angles less than pi, close to pi, but less than pi, that's quadrant 2. And in quadrant 2, what do you know about sine? Is it positive or negative? Positive. Sine is positive in quadrant 2. So that means sine of theta is positive. So here we're dividing by something that's getting close to 0, but with positive numbers. Yes? But now the top is a negative, the bottom is a positive. So this fraction is what? Is it positive or negative infinity? Be negative because it's negative divided by a positive. You understand this? So if you want to be more precise, the actual answer here would be negative infinity. Okay? For that little value there. So in here you know that it's really this one. But again, it's not going to change the outcome. The answer will still be 0. Okay? That's why I said we don't really care for this problem because all we care about is that the bottom is some type of infinity, but then 2 divided by some infinity, that's 0 anyways. Okay? So there's no need to spend time figuring out. But if the question would have been this, find this limit, the limit of cotangent as theta approaches pi from the left, you need to know how to do this analysis. So that's why I'm explaining this. Did you understand why it's negative infinity? Do I need to explain this again? You have to figure out the quadrant of the angle. Because that's how you can tell what happens to sine. Is it positive or negative? To the left is less than pi, quadrant 2. Quadrant 2, sine is positive. If it would have been from the right, what quadrant are we? If it was from the right, what quadrant are we? Quadrant 3, because theta will be bigger than pi, right? An angle bigger than pi is quadrant 3. And what do you know about sine quadrant 3? is negative. So when you take the limit, negative divided by negative is positive. So the answer would have been positive infinity. Do you understand this? All right. Anyways, as I said, doesn't matter here. Here we just 2 over some infinity, that's just 0. So the answer here is 0. There are little calculations that are done in this type of limits. It's mostly analysis. You just need to analyze the function. Okay? All right. Questions? No? Okay, good. Let's see. Let's do, I guess, a couple more. What's the limit as x approaches 0 from the right of 3 times natural log of x? So here plugging in doesn't help much because ln of 0 is not defined, right? The domain of ln is greater than 0, from 0 to infinity, right? So what do we do? Remember, what question are we asking? What's the behavior of this function when x is close to 0, right? That's what we want to know. What happens to this function when x is close to 0 from the right? And, if you're out of ideas, maybe this is a function that you can graph. If you can graph, don't forget what we're doing. So if you know the graph, graph it, okay? We know the graph of ln. So you cannot ignore that entirely because that's going to help you in some cases, like here. So what's the graph of ln? Remember, you need to know your basic graphs. Looks like this, right? I explained this on Friday. This is on the notes, so if you skip over that, then you should go back and watch it. I explained the graph of exponentials and logarithms, and I spent some time on it. Okay, here it is. So remember, exponential functions, it depends on the base, right? If the base is bigger than 1, it looks like this. If the base is less than 1, it looks like this. Why is this important? Because when you take limits, this tells you what happens when x approaches negative or positive infinity. You're going to need this information for infinite limits, okay, for exponentials. In the case of logs, remember the log is the inverse of the exponential, so you have to reflect about the line y equal x. Again, it depends on the base. If the base is bigger than 1, this is the picture. If the base is less than 1, this is the picture, okay? When you have ln, you are in the case in which the base is e, right? So it means bigger than 1. So the graph of ln is the red graph. And if you look at it, what happens when you get close to 0 from the left and from the right? From the left, there's nothing. If you get close to 0 from the right, what happens to ln? It goes down to negative infinity. Do you understand this? And we get that by the graph. You need the graph to be able to do this type of problem. Okay? All right, so then we're going to use that knowledge now because this is the graph of ln, y equals ln of x. And what's important is that when you get close to 0 from the right, it goes to negative infinity. So here we have 3 times something that's going to negative infinity, so the whole thing is going to go to negative infinity as well. Do you understand this? So 3 times negative infinity, that's just negative infinity. Questions? Once again, no calculations here. You just need to know this. So you need to know your basic graphs so that you can do this type of analysis if needed. Okay? Okay. Questions? No? Okay. How about 2 minutes? All right. So couldn't define vertical asymptotes today, but that's okay. We will do it on once. Okay. How about this one? What is this? What is it? Negative infinity. Good. So everybody sees? When you approach zero, this part here is a zero, right? Now this one, what does 1 over x do? You approach zero from the left, so this approaches zero from the left, so it's some type of infinity. Which one? Negative infinity, because the bottom is negative. Yes? X is less than zero. So here, x is less than zero, so that means that this guy here is going to go to negative infinity. This one goes to zero. 0 plus negative infinity, that's negative infinity. Are you okay with this? All right. So next time we're going to talk about vertical asymptote. For example, this means that this function has a vertical asymptote at x equals 0. That's how we define vertical asymptote. Whenever the limit as x approaches a number from one of the side at least is either positive or negative infinity, it means x equals that number is a vertical asymptote for the graph. Okay? Then we're going to talk about horizontal asymptotes, which will be limits at infinity. That's what happens when x approaches infinity. Okay? And then we're going to discuss another technique for limits, which is called the squeeze theorem. There are some limits that we still cannot compute. Like, for example, something like this. As x approaches 0. When x approaches 0, we figured out last time on Wednesday that this limit did not exist. But what if we look at this function? It will turn out that this limit will exist and will be equal to something. But we cannot compute this for conventional means because 0 times something that doesn't exist, what is it? Okay, so you cannot use properties. This is the technique called squeeze theorem that we're going to discuss next time. And this is going to help us for some special limits. And then we talk about continuity. Okay?